Video with subtitles is a great source for large-scale visual textual representation learning. However, the natural long-term videos from the internet have alignment problems. Let's watch a video clip, for example.
If you turn the oven down really low, you can leave them in overnight.
To be honest, the longer you leave them, the better they taste.
Once you've seasoned them with salt, sprinkle over with some sugar.
There are some common alignment problems in this example. First, the video and the text descriptions are usually not semantically synchronized. In other words, they are misaligned. Second, many of the texts are unrelated to the video. For example, describing food taste and explaining reasons. These texts are not visually alignable. Our goal in this paper is to create a model that can do two tasks. First, determine whether the texts are visually alignable or not. Second, if the texts are visually alignable, determine the corresponding video timestamps. The main challenge of our work is that we do not have the ground truth labels for either the alignability or the corresponding timestamps. Additionally, we aim to learn from the noisy web-scale dataset How-to-100M, which consists of YouTube videos. These uncurated videos have substantial noises from both the visual side and the textual side. Before explaining our method, let's imagine what if we have the ground truth labels. Given a long video and a list of sentences as input, we can first extract the visual and textual features. If we have the ground truth corresponding timestamp for each text, we can train the model with an info NCE loss. In detail, the corresponding visual textual feature pairs are the positives, and the other visual textual feature pairs are the negatives. Furthermore, if we have the ground truth labels for the alignability, we can simply train a binary classifier with the ground truth labels. The main idea of our method is to determine pseudo-labels to approximate the ground truth labels and learn from that. Our model has two components. The first component is a visual textual dual encoder. In this component, the video and text encoder do not communicate, and we train them with an info NCE loss on the noisy ASR timestamps. Intuitively, because the video and text are encoded separately, and some texts, like "it tastes good," occur with many different video clips. After training with the info NCE loss, the text-video similarity will still be very low. As a result, dual encoder can filter out non-alignable texts. The second component is a visual textual joint encoder. In this component, the video and text are jointly encoded. Same as before, it can be trained with an info NCE loss on the noisy ASR timestamps. Intuitively, the model already knows the set of sentences to align with the current video, so the joint encoder might give more accurate timestamps. We can determine the pseudo-labels from the mutual agreement between these two complementary architectures. In detail, the pseudo-labels are obtained by merging the predicted visual textual similarity maps from both encoders. We use the pseudo-labels to continue train the dual encoder and the joint encoder to improve both of them. Note that we use an exponential moving average of the model, so the pseudo-labels can slowly update when the encoders get stronger. As mentioned before, the subtitles from the web videos contain lots of noise. As a data pre-processing, we clean up the text by restoring the punctuations and use the full sentences in our work. To evaluate the alignment performance, we manually annotate a subset of How-to-100M. Note that this HTM aligned dataset is only used for evaluation and not used for training. This is an example video from HTM aligned dataset. We can see that most of the sentences are not visually alignable, and for those alignable ones, their visually corresponding timestamps are usually not their original timestamps. This is a zero-shot qualitative result of one video in HTM aligned dataset. From top to bottom, it shows the manual annotation, the output of mu NCE, and the output of our TAN. We can see our model gives a clear timestamp prediction and also a correct alignability prediction. We also evaluated the TAN on zero-shot text-to-video retrieval task on UCook2 dataset. Our network outperforms previous works on this benchmark. Lastly, since the output of our TAN are auto-aligned video-text pairs, we can use this data to improve the backbone visual feature. In this case, we can remove the transformer and simply fine-tune the visual backbone with an info NCE loss. We show that after a quick fine-tuning, the quality of the visual backbone is improved because of this auto-aligned video-text paired data. Thank you.